So some of you might be looking at my first slide and wondering if I made a typo, and I was actually meant to say 341, but I actually don't mean to say 341. I mean to say 342. We'll talk a little bit about it, but just for those of you who aren't familiar with 342, because it actually has not been published yet, although it has gone through public review. 342 is essentially the portion of ASCE 41 on evaluation and retrofit that applies to steel systems. So AISC now has their own manual addressing evaluation and retrofit of steel systems that works in tandem with some of the analytical and other work that is and recommendations that are in ASCE 41. So we'll talk about that in a little bit. So before I go any further, I want to acknowledge a couple of people. So on that first slide, you saw Charles Roeder. He and I have been working on brace frames together for about 15 years, maybe a little bit more. Jeff Berman has done some work with us, and Andrew Sen, who's a faculty member now at Marquette University, was a postdoc and a PhD student who worked with us, and a lot of this work is his. This work has been funded by a number of different granting agencies. We have 3 grants from the National Science Foundation is listed here. The American Institute of Steel Construction has also donated money for us to conduct this work, and they've also organized material supplies for us, especially the tubes. So there are a lot of industry sources that have been kind enough to donate those materials. It just, unfortunately, large-scale experimental work is very expensive. So we're very grateful for the support of these agencies. You'll see that we also did some tests at NCRE, which is the National Center for Research in Earthquake Engineering at the National Taiwan University, or near the National Taiwan University in Taipei. And Casey Tsai is our collaborator there, and we're certainly thankful for his support and input into all of this research. We've had a lot of students on this project, and I'm very grateful for all that they have done. They really worked hard in the lab on the computer and learned a lot about behavior of steel, which I think is critically important when you think about evaluation and retrofit of any system, be it for seismic or non-seismic regions. When we know we have inadequate lateral capacity, be it strength or deformation, we need to be able to evaluate that in a reliable way and also be able to retrofit that. And that is exactly what this talk is about. So I'm going to give you an outline of this presentation because it's quite long, and we're going to go through a lot of different aspects of brace frame design. So we're going to start with the codes and look at what currently is required for concentrically braced frames, especially SCBFs, so special concentrically braced frames. And then when we're going to switch and look at some older brace frames and understand what the seismic deficiencies of those frames are. We've conducted an infrastructure review to understand that. And then I will present the experimental results, primarily 1-story and 2-story tests that we've conducted in our own lab, as well as I said at NCRE. And then, of course, if you're going to evaluate a system that's existing, you need to do some type of analysis to understand what the demands are. And so we have developed nonlinear analytical techniques that we've then used to simulate a number of different buildings. So I will present that research as well. And then we will get to what we actually have put into AISC 342, which is titled Seismic Provisions for Evaluation and Retrofit of Existing Structural Steel Buildings. So if those of you who are familiar with AISC 41, you can see that essentially you'll see we've just pulled out Chapter 9 and expanded on it quite a lot. And I'll give a short example application, and then we will have time for questions. So let's start out with what most of us know, which is the design of special concentrically braced frames using AISC 341. So there are multiple objectives when we think about seismic design. We want these systems to be able to remain serviceable and functional without really any structural and non-structural damage during frequent earthquakes, because of course we want these structural systems to be able to be used. During a larger earthquake, sometimes called an intermediate earthquake, a 500-year event, we do permit inelastic action in our structure, but we really do expect that the structure will be occupiable and potentially will need to be repaired, hopefully won't need to be repaired after that event. And then the third earthquake that we think about is this maximum credible earthquake. A lot of times we refer to that as a 2,500-year event. And that's an extreme earthquake. And that in that earthquake, we expect to have significant damage, but a very low probability of collapse. And with the work that we've done, which I'm not going to present here, SCBFs do satisfy that. They are not a collapse risk.